So we'll kick off chapter 7. This technique is called substitution. It's a real powerful technique when it comes to integration. It allows you to simplify what might look like a pretty complicated integral to something that's a lot simpler. Okay, I'm going to jump right in and show you how it works. All right, this one is not so bad. The square root of 3x plus 2 dx. All right, I'm going to start you out with an integral that's fairly simple, but then show you how this technique allows you to work with increasingly complex integrals. So how substitution works is you look at the function that we're integrating. We recognize it's a function within a function. Okay, it's something within something else. We call those composite functions. And so the two functions we've got combined into this problem, okay, that part right there is what's called the linear function. And that's inside of what other kind of function? A square root. Okay, so it's a linear combined with a square root. We call this a composite function. And so your job first is to recognize composite functions within an integral. Once you recognize a composite function, you always take the interior function, the one that is inside of the other, and you reassign it to the simple substitutionary value of u. This is called u substitution. And so we're going to take the letter u, and we're going to assign that to the interior value, the interior function of 3x plus 2. Okay, this technique is called u substitution. It's always the inside function. Once you've assigned u, or chosen your u, you will also find out what the derivative of that u choice was. And this is a pretty simple one, and so what is the derivative? Just the number 3, right? Now that derivative can be manipulated. The du and the dx and the 3 are all the working parts of that, so we could rewrite that as du equals 3 dx. In other words, you just multiplied both sides by dx. And then you can rework that as well and rewrite that so that dx is alone and du over 3 equals dx. So there are 3 versions of that, all with the different parts being alone. Notice the first way I wrote it, 3 was by itself. The second way I wrote it, u was by itself. The third way I wrote it, dx is by itself. And that's where you want to end up. You want to end up in the position of dx being by itself. All right, now this is like the pre-work that you do. Here's now the work of the problem, where you're going to show good equal signs and good form as you do it. All right, so the question starts like this. 3x plus 2 dx. Okay, equals, dx equals. We are going to replace the 3x plus 2 with the letter u. So that is replaced. We are also going to replace dx with what we just found that dx is the equivalent of. So we got dx by itself right here. Okay. And so we want to get that alone. And so we can replace that with du over 3. Okay, so that is called substitution. We just substituted 3x plus 2 for u, and we substituted dx for du over 3. Okay, continuing with our good form of equal signs, we know that 3 is a constant in the denominator, so I can pull 1/3 out to the front. Okay, dividing by 3 is the same as multiplying by the reciprocal, so I can pull that out front. The rad of u, I'm just going to write as u to the half, du. And now we have a straightforward integral in terms of u. So there are no more x's in the problem. This is only a problem with u. And so now we can do our technique of regular antiderivative. So u to the half becomes u to the 3/2 divided by 3/2 or multiplied by the reciprocal 2/3 plus c. If we clean that up, we're looking at 2/9 of the square root of parentheses u cubed. And your final step would be to undo the substitution you did at the beginning. U was chosen to replace 3x plus 2. So now we want to put 3x plus 2 back in. And so 2/3 of the square of the quantity 3x plus 2 cubed under the square root plus c is the antiderivative of the original problem. So u allows you to work temporarily in a different variable that is simpler, and then at the end you make one final unsubstitution to replace it back to what it started with. Okay, any questions about that particular one? Yeah? Oh, I shouldn't have. It should be 2/9. Thank you. Glad you caught that. All right, let's try another one. All right, so the integral of the cosine of 5x minus 7 dx. So we recognize this as being a composite function. It is an interior function and an exterior function. So once you recognize that, then you identify that this is going to be a time for me to do a u substitution. And so you make your choice. What should we choose u to represent in this question? What is the interior portion? This is like actual question I'm asking you out loud. Okay, we want 5x minus 7. Once we've made that choice, we choose it because it is the interior. We have a trig function and we have a linear function. We choose the linear. Then we find du dx, the derivative. That's simply the number 5. We rearrange that so that du is 5x. And we rearrange that so that, whoops, du, hang on, I left out my d. Du is 5 dx. And then I'll rearrange that so that dx is by itself, and I have du over 5 equals dx. You always want to end up with the dx part alone, because that's what you're going to change out in your original question. All right, so my work goes as follows. That was the pre-work. All right, equals. So my question now equals. I keep the cosine, but I change what's in the parentheses to u. I also change the dx to be du over 5. And now you'll see something very similar happening to what happened last time. We're going to pull out the constant as 1/5 on the outside of the cosine of u du, which is a very simple integral. So this process simplifies something. It takes your original integral and makes it simpler. Then we have 1/5 times the antiderivative of cosine, which is negative sine of u, plus the constant c. And now you want to unsubstitute what u originally stood for. And so now you're looking at negative 1/5 of the sine, and u was chosen to replace 5x minus 7 plus c. So the u substitution method works awesome. Yeah. Oh no, what? The antiderivative. Yeah, I just need to look at, yeah, you're right. I'm just not even looking off my notes. Yeah.
Does the 1/5 not carry over to the C as well? Does it not like distribute?
Oh, well, yes, technically, but 1/5 times a constant is a new constant. If you would like to call this now C1 or something, but it's still a constant. So typically, when we double a constant or if it's still a constant, we just still call it C, yeah. It's like if you double infinity, it's still infinity. We don't write to infinity. Okay, so this works awesome on composite functions. It also works great on products. What rule did we have for derivatives when we encountered products? The product rule, okay, yeah. That was for derivatives. There is no product rule for antiderivatives. You have to do a different technique. So one of the techniques that works well on products is substitution. When that doesn't work, we have another technique that we'll learn later this chapter. But I'm going to show you one that works with products. All right, here we go. The integral of the product x times the sine of 2x squared dx. So when you have a product, your first inclination should always be to try a u substitution to see if it cleans your product up. Because you cannot just take the antiderivative of each piece, just like we don't take the derivative of each piece. You need a special rule. And the rule is u substitution. But your u choice should still always be the thing that's inside, which would be what in this case? 2x squared. All right, so we are going to choose u to be 2x squared. Don't worry about the x on the outside. You choose what's on the inside. Your du dx is now a little bit more interesting than it has been before. The derivative of 2x squared is 4x. Okay, well, now we start to manipulate that around. So du would turn into 4x dx. And then we manipulate that one more step farther and we get dx alone. So du would be over 4x, and that's equal to dx. All right, now I'm ready to do my work. So x times sine of 2x squared dx. You are only substituting in two places, not multiple places, two places. We are only substituting inside the parentheses, and we are only substituting for dx. Do not worry about the x that's sitting out front. You'll see why. So we're going to leave that x just there times the sine. Now we're going to substitute. Inside of the parentheses becomes the simple value of u, and the dx gets replaced with du over 4x. Do you see why now I didn't have to worry about the x that was sitting out front? So what's going to happen to it? Not cancel, but the word is, we were looking for the word reduce, okay? Yeah, so we're going to actually reduce the x's. And so we didn't have to worry about that x that was sitting out there. It will reduce away with the single x. Now I can pull the 1/4 fraction out, and I'm left with the simple antiderivative sine u du. Now this one is negative cosine u plus c. And then you can change the u back, or you should change the u back, so negative 1/4 of the cosine of u, which was chosen to stand for 2x squared, plus c dx. How do you check your work on a technique like this? Any ideas? What would happen if I took my answer and I did the derivative again? What should I end up with? The original thing I started with. Okay, so that's always a good idea to check your work. If I was taking the derivative of this, okay, d dx, and I was taking the derivative of negative 1/4 cosine 2x squared quantity plus c, the derivative of that would be negative 1/4 times negative sign, which would be positive sign. And what would I have to remember to do? Okay, chain rule, which would be times 4x, and then plus c is 0. And when I clean it up, the 4 here and the 1/4 there, and I've got this x at the backs, which I put in front, so x sine 2x squared, which is exactly the integral that I started with. So that would be how you could check your work, is by retaking the derivative again. It's the chain rule that produces that x out in the front, which is the original product. So when you're doing an integration, an antiderivative that has a product, you know it came from somebody's chain rule at some point. Okay, so this was just a quick way to do a double check to make sure that you hadn't made an error in your antiderivatives. Okay, try again. It's all about choosing the right u. Okay, here we go. All right, let's try parentheses 1 minus cosine of t over 2, end parentheses, and another set of parentheses square times the product of the sine of t over 2 and that parentheses dt. All right, here we go. Not only do we have a composite function where you've got one function inside another function, we also have a product function. So we've got a little bit of everything. You need to choose what you're going to substitute as your u choice. Okay. All right, so I'm open to yes.
What happens if like the stuff inside two cosine is different from the stuff inside the sine?
Oh, you need a different technique. Okay, yeah. Okay, with that said, what should we choose for our u? So I'm open to suggestions. Okay, so t over 2 would be a suggestion. And why'd you choose that? Okay, so they both have it in common. It's also in the inside parentheses. Okay, all right, so we can go with that. And so then my du dt this time, not du dx, would be what, Luke, if you were just working with t over 2? Or are you doing the quotient rule?
Oh, yeah, so 2 over, at the bottom of the quotient rule.
Okay, but I'm going to suggest, how about you just say that's 1/2 t, then you don't have to use the quotient rule. So what's the derivative? You're making it harder than you need to do.
I'm sure it's super easy.
Okay. What's the derivative of 1/2 x? Yeah. All right, derivative's 1/2. That's all we need. It's just a constant. Yep. All right, so we want to manipulate that. We want to move du to be 1/2 of dt. And then we want to get the dt by itself. So we multiply both sides by half, so it gives me 2 du equals dt. So now we're going to substitute. So the original question, 1 minus cosine of t over 2, that quantity squared times the sine of t over 2 times dt becomes 1 minus cosine of quantity u, that quantity squared times the sine of u times 2 du. What I end up with should be simpler than what I started with. That doesn't look any simpler to me. Because nothing reduced. Something should reduce, especially if you have a product. Okay, the product is built because it's somebody's chain rule. And so that means if nothing reduced here, that the U choice at the beginning was not right. So I'm sorry, Luke, I let you go down a path, but that's a good experience to know, okay, well, now I'm stuck because I'm no better off than what I started with. I still have a composite function. I still have a product, so that U choice was not the right one. So let's look back at the beginning. You chose it because it was in parentheses, okay? Well, isn't there something else that's also in parentheses? Go ahead, Joel. Yeah, choose this whole thing. 1 minus cosine t squared is also in parentheses. And not coincidentally, the product next to it has a sign in it, which is the chain rule part derivative of negative cosine. So it's not, they're designed that way. So let's try and see if that one's any better. All right, so we're going to do take 2, and we're going to choose u to be 1 minus the cosine of t over 2. So then the du dt is the derivative of that. So the derivative of negative cosine is positive sine t over 2. And the derivative chain rule of that is 1/2. That's looking better because it's got the part of the product in it. Okay, so then we're going to bring the dt, so du by itself would be 1/2 sine t over 2 dt. That's the du by itself. Then dt by itself would be 2 du, so multiply everything by half, and then divide by sine t over 2. And that's dt all alone. So let's put those things into the original integral and see if that helps me out at all. So I've got the original integral, which was 1 minus cosine parentheses t over 2, that whole quantity squared, times the sine of t over 2 times dt. I am going to replace inside the parentheses here with u, and I'm going to replace the dt. We only make 2 changes. Don't worry about the sign in the middle. It will take care of itself. So this will equal. The first arrow we're replacing with u. It's cleaner already. I'm not doing anything to the sine of t over 2. And then my second arrow is getting replaced with 2 du over the sine of t over 2. So I did not do anything. I was comfortable leaving the sine of t over 2 there because I knew once I made that was the thing that was going to reduce. Something has to reduce, and that was it. So that leaves me with the only constant is 2, which I can pull out front, and I'm left with u squared du. So that is significantly simpler than the original question. So the antiderivative of 2u squared is 1/3 u cubed plus c. And then I can change that back to 2/3, change it back to the choice that I made, cubed plus c. And that is the final answer. And you check your work by taking the derivative again to see if you start out with what you have. For the first chunk of your homework assignments, they tell you what to choose for u. Here's the question, and u is blank. Here, practice, practice. The second half of your homework, the responsibility of picking the u is then on your choice. Okay. So you get kind of in the habit, oh, that's what they picked. Oh, that's what they picked. And then maybe you start to see, oh, that's why they picked it. Oh, because it reduced. Oh, that's why they picked that. Then when you get to your choice, your turn, you have a little bit of experience. Okay, last one. right, the integral of dx over the square root of 5x. This is still a composite function, something inside of something else. It's not a multiplication problem this time, it's just a straight out composite. Okay, what should we choose for our u? Jason, you want to help us out? Square root of 5? Okay. Alright, so square root of 5 x. Okay, so why'd you choose that one? Okay, so tell me how you would rewrite it so it would be inside. Tell me what you're thinking.
So like, wouldn't it be 5x, like square root of 5x and negative 1?
Okay, okay. So, square root of 5x to the negative 1 dx. All right, so you're choosing that because it's inside the parentheses. Could be written inside the parentheses of 5x. Okay. All right, so just for sake of time, I'm going to stop him because it's not the right u choice. Okay, but he is totally on the right track about thinking about what's inside of something else. All right, is there a different way to write that? Go ahead. No? Yeah, Abby. There we go. Quantity 5x to the negative 1/2. Okay, that's how you want to think of this question. Okay, so the problem just with the way Jason had it is inside his parentheses, he still had two different kinds of functions. He had a linear and a square root combined at the same time. Okay, you need to get down to where you've got just one single, so the 5x is the thing that's inside of, and then rewrite your square root as a power as well. So that'll just be a better u choice. So I'm going to come over here and just erase the square root that Jason had, but we'll take our 5x as our u because it is inside. Okay, all right. So moving forward with that, now du dx, the derivative, is just the constant 5. Manipulating things and moving them around, du is 5 dx, that's multiplying both sides by dx, and then dividing both sides by 5. We end up with du over 5 equals dx. So now we're ready to make our substitution. So the parentheses 5x, which is now written to the negative 1/2 power, we're making two substitutions. We'll do it for the inside the parentheses and the dx, and those will be the two substitutions we make. So this becomes parentheses u to the negative 1/2, and it becomes du over 5. We can pull the 5 out to the front as a 1/5, leaving me with u to the negative 1/2 du, which we're ready to do the antiderivative on. So 1/5 quantity, u to the now positive 1/2, because I add 1, and then multiply by 2. So we end up with 2/5 times the square root of u plus c. So the final answer is 2/5 times the square root of the 5x that was originally chosen plus c.